In this second guide, I'm going to explain how to run the factorial 2x2 Bayesian alternative to ANOVA. In this data set, I've got 80 participants who were classified according to their social and economic views. So social views and economic views are the two independent variables or factors. So half of them have liberal views in social views, so these are 40, and 40 have conservative views, social views. In terms of economic views, half of the liberals believe in the state has to be big, and half of them believe it should be small, and the same with the conservatives. Half of them believe in the big state, and half of them on small state. So the variable that we measure, the dependent variable, is how much they agree with the new tax to improve or reduce poverty. So we've got here for each participant what percentage of agreement from 0 to 100. Okay, so we do descriptives. We cannot do too much in descriptives because we can only split by one variable. Here we've got two variables to split, so we are going to see the descriptives when we do the ANOVA. But we can have a look at tax agreement, the whole, or the total mean. We can see that the total mean is 47.487, and that gives us an idea because of the linear model that we use for the ANOVA uses as reference the total mean. Okay, so let's go to the ANOVA and Bayesian ANOVA. So it's the same as the one-way ANOVA. The difference is that we are going to have two factors instead of one factor. So dependent variable tax agree, and fixed factors are social and economic. We don't have random factors. And we already have the base factor here. Before explaining this, let's go to some descriptives. So if we take descriptives with credible interval, we have there the descriptives. So we've got for conservatives that believe in big state, 57.05 agreement. Those who believe in small state, 36.65 agreement. Liberals that believe in big state, 60.25 agreement. And the liberals who believe in small state, 36.0 agreement. These are the standard deviations, number of observations, and the 95% credible interval of the posterior distribution. Right, so we can also have the plots of the model average posterior, so the posterior distribution and average across the 5 models, but weighted differently according to their posterior distribution of the models. So let's see that plot. And we've got here, if we compare the conservatives versus liberals, they don't vary too much from the total mean, which would be 0. But when we have big state versus small state, that makes the difference. So the social views are not related to how much they agree with the tax. Their economic view has an effect on their agreement to a new tax. Okay, so this one, it contains the 4 conditions, and there is a lot of overlap, so it's not very useful. Okay, so let's start now looking at the table of base factors. So we start with 5 models. The null model, that says that the prediction will be they use the beta 0 as the mean total, the one I showed you before. Then there is a model that says that the economic views affect performance. The agreement. Another model that says that social only, and then the model that includes both variables, social and economic. And the fifth model includes the social, the economic, and the interaction between the two variables. So we've got 5 models. The probability of the model, we want to have an equal distribution, so we don't give more credence to any of the models. We give equal credence, and because the sum of these has to be 1, then we have to assign 0.20 to each of these models. That's the probability of the model before observing the data. Now, when we observe the data, the probability of the model after observing the data then changes. So, the probability of the model after observing the data for the model that says that the economic views are important, only the economic views, it went from 0.2 to 0.69. The model that says that both variables are important went from 0.2 to 0.199. So it remained the same. The model that says that the social, the economic views, and also that predicts an interaction went down from 0.2 to 0.109. The null model went down dramatically from 0.2 to 1.629 e minus 19. So remember, it's 0.181629. And the model of the social that says that social views are important, only social views, not the others, it went down even more from 0.2 to 4.089 e minus 20. So 0.19404089. So we've got BFM. That BFM, what it does is to calculate the prior odds and the posterior odds. So prior odds are for each model are calculated as follows. So for the economic model, the probability of the model is 0.2, and the probability of the sum of all the other models is 0.8. So the prior odds is 0.2 divided by 0.8, which is 0.25. Okay, so that's the prior odds for this model. In fact, it's the same for all the models. It's 0.25. The posterior odds are for the economic one, for example, is 0.692 divided by the sum of the probabilities of all the models. And remember that these 5 probabilities must add to 1. So if we've got 0.692 for the economic, for all the rest of the models will be 0.318. So the posterior odds for the economic model is 0.692 divided by 0.308. 308, not 318. 308. So that's the posterior odds. And BFM is the posterior odds divided by the prior odds. And that's 8.988. So the same applies for all the other models. So BFM is a comparison of the current model versus all the other models. Now, this is typically the column that we are more interested in. Now, we have to take into account 2 things. First, what base factor we are using, BF10 or BF01. BF10 compares the probability of the alternative hypothesis over the probability of the null hypothesis. So it will compare, in this case, the model that says that the economic views are important versus the null model. So that's That's one possibility, but actually it's not what's happening now. I need to explain this. In this order, we have to decide whether compare to best model or compare to null model. So we need to BF10 means different things depending on what we tick here in order. So at the moment is comparing to the best model, but the option is compare to the null model. So in compare to the best model, what it's doing is to do in a base factor between the model presented in the line and the best model. What's the best model? Well, the model with a higher posterior probability of the model given the data, and in this case is economic. So economic is the best model. So the BF10 here is going to be a comparison of the model economic versus economic, because economic is the best model. That's why base factor is 1, because it's dividing this probability 0.692 divided by the same number, so that is 1. In social and economic, so the two variables, the base factor is 0.288, because what it's doing is 0.1993 divided by 0.692, and so that's the base factor. Then base factor 10 for the third model, the third best model, social and economic plus the interaction, that has a probability of 0.1087, and divided by 0.692, that is 0.157. So as you can see, when you compare to the best model, the base factors will be lower than 1, because if they were better models than the best, they should have base factor more than 1. But obviously, because they're worse, they should have a base factor less than 1. And the null model and the social model, the base factor is very, very low. So their probabilities are very, very low. Therefore, when you do the ratio of this number divided by the best model, it will be a very low number as well. Right, so if we tick compare to the null model, what happens is that now null model is on the top, and all these comparisons by BF10 are the model that you are comparing versus the null model. So in the first row is null model versus null model. Then again you've got the base factor of 1. When you compare economic versus the null model, you've got a base factor of 4.247. When you compare social and economic with the model, you've got a 1.22, and followed by so it's a number with 18 integers, and social plus economic plus the interaction, a number with 17 integers, and social is even lower than the null model, 0.2510. So then we can see the effects. So before we do that, how do we interpret this? we interpret that the economic model is much better than the null. Social and economic is also better than the null, but worse than economic alone. So let's return to compare to best model. So when you compare social and economic versus the best model, that model is 0.228 Bayes factor, so it's lower than the economic. So now if we want to know how economic, how much better it is in comparison to each of the other models, what we do is to change BF10 to BF01. So this will put in, so instead of putting in the numerator and all the other models and economic in the denominator, if we put BF01, it will put economic in the numerator and all the other models in the denominator. So that will tell us how much better is economic over the others. Okay, so economic versus economic is not better at all, it's the same. But when you compare economic with social plus economic, the Bayes factor is 3.47. So that means that with the variable economic alone is a better model than if you add the social variable as well. And if you add social and the interaction, Bayes factor in favor of economic is 6.3. And of course, economic versus null, it's a number with 18 digits, and versus social is a number of 19 digits. So that's telling us that the model with the variable economic views only is the best model. And it is 3.5 times better than the model with two variables. Okay, so now we can see the effects. So when with the table of effects, as I explained in the one-way ANOVA, it compares the variable social. The variable social appears in three models: in social plus economic, social plus economic and interaction, and social. So because it appears in three models, then the prior probability for social is the sum of the probabilities of those models. So 0.2 plus 0.2 plus 0.2, that's 0.6. The variable economic also appears in three models: economic alone, social and economic, social economic, and the interaction. So likewise, it has a prior probability of 0.6. And the interaction appears in only one model, the model with the interaction. Therefore, the prior probability is 0.2. And after observing the data, the posterior probability for including the variable in the model is for social is 0.308, for economic is 1, and for social and economic interaction is 0.1087. So this, what it does is to add the probabilities, the posterior probabilities that were of the models in which the variable is present. So social, the posterior probability is 0.308 because it's adding the posterior probability of social plus economic, 0.199, the posterior probability of social plus economic and the interaction, 0.1087, and the probability for social, which is very low number. So adding all these three values That's 0.308. For economic, it's 1, so the probability of inclusion is 1, because it's adding the probabilities of the 3 models in which the variable economic is available. So in economic, 0.692 plus 0.199 plus 0.1087, and it's 1 because these two numbers are very, very close to 0. So in the models in which the economic views are not there, the probabilities are almost 0, so the sum of the other 3 is almost 1, and at least to 4 decimals the better approximation is 1. Okay, so then the base factor, now we have base factor exclusion. That's because I used base factor 0.1, but if what we are interested is in the inclusion, so I have to use base factor 1.0, and that it appears now. So the base factor inclusion, what it does is to calculate the posterior odds divided by the prior odds, and that's the base factor. Remember that the posterior odds are calculated 0.308 divided by 1 minus 0.308, which is 0.692. And that is divided by 0.6 divided by 6.4, which is 1.5. And that gives us 0.2967. The posterior odds for economic is almost infinity, so it's 1, but it's actually not 1, it's 0.99999 divided by 0.00001, something like this, and that is a number with 14 integers, and you divide that by 1.5, which was the odds before collecting the data.